Hi. You must have heard of eigenvalues and eigenvectors, and probably you also know how to calculate them, basically the mathematics of how to do that. But this lecture is not about that. This lecture is about giving you a physical intuition on what exactly are eigenvalues, which are denoted by lambda, and eigenvectors, denoted as v. So let's start with something that all of us are very familiar with, most likely. Let A be a matrix, lambda, let it be a scalar, and V be a vector. So if AV equal to lambda V, let's say that condition is satisfied, that means we can also write it as AV equal to lambda times I times V. And here I is the identity matrix. So now both of the sides are matrices, so you can bring the right hand side part to the left hand side, because now lambda I is a matrix and A is also a matrix. So we can now write this as AV minus lambda I times V equal to 0. And this can be written by grouping A and lambda I. So A minus lambda I times vector V equal to 0. And you would already know what is usually done in situations like this to find the values of lambda which satisfies this. So we write determinant of A minus lambda I equal to 0. Do you know what is the reason why determinant of A minus lambda I equal to 0 in this case? Of course, we know that we don't want the trivial solution. We know that we don't want A minus lambda I equal to a null matrix or vector V as a null vector. That will be the trivial solution. But we want something that is non-trivial. And have you thought of why this is the case? If you don't know why, what is the physical meaning behind this, we will cover that in this lecture so that you will understand actually why this is done. But we can do the mathematical calculation which will allow us to find the value of lambda such that determinant of A minus lambda I equal to 0, that condition is satisfied. And let's say lambda 1 is one such values which satisfies this condition, then we can find a corresponding vector V such that A times A minus lambda I times V equal to 0. So the condition that we are looking to satisfy ultimately is AV equal to lambda 1 times V. So this is the slide where we just very briefly discuss how we ultimately calculate this vector V, which we usually call as the eigenvector. But mind you, you already know this most likely, but whether you know this or whether you don't know this, the goal is not to go through this math part. It is probably easy, but the goal is to understand why we are doing this. Why does this make sense, right? So if A is the matrix, which can be denoted like this, A11, A12, let's say those are the elements, 2 by 2 matrix, then we can write like this. If V vector is like a 2 by 1 vector, AV equal to lambda 1 V, and then we can solve for X and Y, which are the individual values of the elements within the vector V. So there are two unknowns X and Y, and there are two equations, and we can solve this to get the solution. Let's say the solution is such that X equal to X naught and Y equal to Y naught. So then the eigenvector is this and eigenvalue is lambda 1. So this is how the exercise is usually done, and I'm pretty sure you have done this yourself if you're watching this video. Even if you have not done this, this is not a hard thing to do. So you may question, this is something that you can easily understand. The math is not extremely hard or anything. So what's the meaning of this? However, like, why do we call something as eigenvalue or eigenvector? Why does it make any sense? Like, what's the physical intuition behind doing all of this? So in this lecture, we'll explore what exactly are eigenvalues and eigenvectors. Eigenvalues famously called or denoted by lambdas. Eigenvectors often used the vector V is used to denote eigenvectors. So this is exactly what we will explore in this lecture. Although you may be familiar with the mathematics behind calculation of lambda and V from this formula, have you thought of how you can define what is eigenvalue and what is eigenvector in simple logical terms? What is in just plain English? Have you thought of how you can define eigenvalue and eigenvector? We will explore that today. So overall, what we want to talk about today is, first, we will look at the importance of unit vector, the unit vector x and unit vector y in two-dimensional space. It's very important to understand the linear transformations of these unit vectors for you to ultimately understand what exactly are we doing when we are talking about eigenvalues, eigenvectors, etc. So linear transformation will be what we'll be looking at after this, and we'll see how this transformation can change the orientation of a unit vector. And we'll specifically look at three operations: scaling, rotation, and shear operation as part of the linear transformation. And then we will look at determinants, but not from the mathematical perspective of, if you have a 2 by 2 matrix, I'm sure you know how to calculate determinant. You multiply the diagonal elements, these two, and subtract the product of the other two diagonal elements. But more than that, we will look at what exactly is determinant in the context of linear transformation, and how does it relate to scaling in one sense. And we will also see a very beautiful physical intuition behind determinant of a matrix becoming zero. So we'll see what that means. And only after this, we will come to eigenvalues and eigenvectors. So this will be the structure of this lecture. We'll first start with unit vector in 2D space. There are two unit vectors, x cap and y cap. So in the 2D xy space, x cap is column vector 1, 0, and y cap is column vector 0, 1, right? These are the unit vectors. And what is the peculiarity of the unit vector? The peculiarity is that we can access any point in the xy space using these two vectors, x cap and y cap. So what does that mean? What it means is the following. So let's say we have a vector that looks like this, this black color vector. Let's say this is the vector that we are looking at. If we place the vector over here, right, over somewhere like this, let's say, this can be expressed in terms of the unit vectors. So how is that? Let's see. So this vector is probably in the x direction it's 5 times as long as unit vector x, let's say, right? So this x dimension is maybe 5, y dimension is maybe 2, right? So let's say this is the vector. So this can be written also as 5x plus 2y. So we can write this vector as the linear combination of the two unit vectors. What if our vector was over here instead of like this? What if it was here? Maybe then the x dimension of this is -4, and maybe -4, and y dimension is, let's say, -2, something like that. I'm being approximate here, not exact. And this can be expressed as -4x minus 2y. Again, so irrespective of where is the position of this xy vector, any vector in this space, in this 2D xy space, can be expressed in terms of these two unit vectors. So we can access any point in the 2D space. So that is the peculiarity of these two unit vectors. Okay. Now, can we do the same thing with any other pair of vectors? So let's say we had these two vectors, x new and y new. Can we accomplish the same thing? Can we express any vector or any point in the xy 2D space in terms of these two vectors? Let's see. So as long as these two vectors are not parallel, like if they are not overlapping on top of each other, we can do that. Let's see how. So in this case, we have a new vector. Let's place it over here, right? And what are these? Earlier, this was a unit vector x and unit vector y. Now we can denote the pink one as x new and blue one as a y new. And now this vector, this black vector, we can represent in terms of x new and y new. So along the pink, maybe let's say this is 6 times x new. and this is not at all oriented along this axis. So now you have to imagine that although I have this, this kind of a grid here, now that because the new vectors that are the axis of my new space are x new and y new, my grid would actually look something like this. So since the x new is parallel to x hat, the x grid lines would look like this, but then the y grid lines would look like this. So this is my new xy plane. This is how it looks like. So so this does not have this vector is 6 times x new plus 0 times y new. It has no y component in that. And what if this vector was somewhere like here? Let's say it's over here. How can we express this in terms of x new and y new? Maybe again, I'm being approximate. So this vector it looks like I have to multiply x new maybe 5 times. I mean minus 5 times. I'm not being exact here, but approximate minus 5 times x new plus. So this is a vector. I should actually. Oh, there is a small mistake here. This is not x new cap. It's just x new vector. It may not be unit vector, so I should not write cap on top of it. So minus 5 times x new vector plus how about y? In y also it's kind of in the negative direction, correct? So maybe this is plus minus 5 y new, something like this. So any vector in the xy space now we can also represent in terms of x new and y new. Previously we saw that any vector we can represent in terms of x cap and y cap, which were our original unit vectors, and now we show that we can do the same thing with x new and y new. So what if the two vectors are parallel? What if x new was parallel or anti-parallel to y new? Basically they align along the same line. Then you can see that if a vector, this black vector, if it is, let's say something like this, then there are a lot of combinations of x new and y new. So this pink is again x new, and blue is y new, and this vector, this black vector, which starts from the origin, it can be expressed as 5x new minus y new. It can also be represented as just like 3.5 x new plus 0 y new. There are many different ways in which we can represent this. But can this vector, how about this? Can this vector be represented in terms of these two? No, it cannot be represented because these two vectors are aligned purely along this axis, our original x-axis, which means these two vectors, no matter how we add these two vectors, how we scale and add these two vectors, we will not get a vector which is out of this line. The resultant vector will always stay on this line. It won't have a y cap component. So all the vectors in this 2D xy space cannot be accessed using these two, pink vector and blue vector. I'll come to why this is so important when you think about transformations. What I'm saying right now it may appear trivial to you, and that is because it is actually trivial. But this same concept, when you view in terms of linear transformation, it has very meaningful implications. So we'll come to that in a moment. So just remember this: any two pair of vectors we can use to access any point in xy space, as long as those two vectors are not parallel or anti-parallel. Okay, so this is where we enter the idea of linear transformation. Linear transformation is probably it forms a big foundation behind the entire linear algebra. So try to understand this really deeply. So first, let us look at matrix multiplication. Of course, you will most likely know how to do matrix multiplication. So let's look at a matrix, 2 by 2 matrix A, denoted by 3, 2 in the first row and 1, 2 in the second row. And let's have a vector P. I'm not putting the vector symbol on top of it. It's not really the point of this lecture, but assume that, I mean, whenever you see a column matrix like this, it's assume that it's a vector P of column 4, 5. Our goal is to get an intuition of what is the meaning of the matrix multiplication A multiplied by B. So we already know that since we are multiplying a 2 by 2 matrix with a 2 by 1 array or vector, the result is a 2 by 1 vector, right? So just like this, let me just write it down here. So this is 2 by 2 and this is 2 by 1. So the size of the column of this is same as size of the row of this. So the result would be this 2 by 1, right? Result of the matrix multiplication of these two. But we are not interested in finding out the result. Of course, that part is easy. You're already familiar with that. But we are more interested in the meaning of matrix multiplication in the context of linear transformation, and why we are calling a matrix multiplication as linear transformation. You will see that. So let's first calculate A multiplied by B, 3, 1, 3, 1, 2, 2 multiplied by 4, 5. So you know how to calculate this. 3 times 4 plus 2 times 5 plus, that will be the first element, top element. Second element would be 1 times 4 plus 2 times 5. So that's what is shown here. So 3 times 4 plus 2 times 5, that is the first element. That is 12 plus 10, 22. The second one would be 1 times 4 plus 2 times 5. That would be 4 plus 10, 14. So, but you know that this calculation is really trivial. I don't think there is anything that you will find surprising here. So you may ask, what's the big deal about this calculation? It's simple matrix multiplication. The big deal is the intuition behind matrix multiplication. So let us look at the same thing once again, but this time focus on the columns of the matrix A. So the first column of matrix A, so I have deliberately used a group of colors so whenever you see the same color, it's because they are part of the same column. So pink is the column 1, 3, 1, and blue is column 2, and that is 2, 2. Now let us look at the matrix multiplication in terms of what is happening to the vector P. So the matrix A is doing something to vector P to get a new vector, right? That's what is happening. So let us see that. And before going into that, let us see what the matrix A does to the unit vectors itself. Because any vector P in the xy plane, we saw earlier that we can represent it in terms of the unit vectors x cap and y cap. So let's see what happens to the unit vectors first. So if you multiply unit vector x with ax cap is 3, 1, 2, 2 multiplied by 1, 0. And the calculation is easy. It's 3 times 1 plus 2 times 0, that is 3. And 1 times 1 plus 2 times 0, that is 1. So do you see what happened here? The matrix A transforms the unit vector x cap in such a way that the resultant vector is the first column of the matrix A itself. So that's why I have denoted it in pink. And what happens to unit vector y? Unit vector y is matrix A when it's multiplied with unit vector y. It transforms the unit vector y such that the result is the second column of the matrix A. So this is a very interesting insight, because you can call this essentially as unit vector transformation. So if I denote the transformed unit vector as x new, so x new is not unit vector anymore. Its length is not 1 unity anymore. So the transformation can elongate the unit vector. It can rotate it. Basically, original unit vector was 1, 0. Now it has become 3, 1. So it has both x and y component. And not just that, the x and y components are not equal. So something has happened to the unit vector x hat, and something has happened to the unit vector y hat. And the transform unit vectors are the columns of the matrix A. So just keep that in mind. And if you really look at what's happening, I'll show that in a moment. if you think about what is the purpose of the unit vector x and y, the original unit vectors x cap and y cap, the purpose was it helped us to define the coordinate system, right? Because the xy grid was perfectly perpendicular when the unit vectors were like in the x direction and y direction. But when we transform these unit vectors, the new unit vectors are now the xy axis. So if new unit vectors are in a different direction compared to original unit vectors, what that means is the xy axis itself is getting kind of transformed into a parallelogram shape, or it won't stay like a rectangular grid anymore. It may look like a parallelogram grid. So since unit vectors define the coordinate system, when we transform the unit vectors, it transforms the entire 2D xy space. I'll just show you that in a moment. So just have a look at this transformation. So now let us look at 3 transformation operations: scaling, rotation, and shear. These are all very simple. I just want you to get a brief idea about this without spending too much time. So if x hat and y hat are these original unit vectors, and let A be this matrix 2 0 2 0. So you can see that these elements are 0, just the diagonal elements are 2, and you can already see what's going to happen to the unit vector x cap and y cap. Unit vector x cap will be the first column of A, which will be 2 times the original unit vector, right? And the unit vector, the new transformed unit vector y cap will be 2 times the original unit vector y cap, and this is what it looks like, right? So why do we call this as scaling? We call this as scaling because what's happening to the vector at the end of the day is just it's getting multiplied by a constant. The vector is not rotating. Nothing else is happening to these vectors. And if you really look at the grid, right, the grid corresponding to the new x and y axis, this is the grid, right? So let me just draw you the original x-axis and y-axis corresponding to the original unit vectors were like this. And since the unit vectors are just getting scaled, maybe all that is happening is the grid is probably getting scaled. That's it. The grid is not like becoming a parallelogram. The grid will still remain like a set of squares. So that's why this is called scaling. And next, let us look at rotation. In rotation, let's say the matrix that is doing the transformation is this. This first diagonal elements are 0 0. The other ones are like this, -1 and 1. So now x new will be 1 times 0 1, and which is 0 1, the first column itself, and y new will be the second column, which is -1 0. So now you can see what's happening to x new and y new. So original x and y was here, and the transformed x new is like a 90-degree rotation in counterclockwise direction of the original x, and the transformed y new or transformed y cap is a counterclockwise 90-degree rotation of the original y cap vector. So here x new, the x and y vectors are not elongating or squishing. It's just rotating. So this whole system just rotated by 90 degree, right? Let me just draw that and show it to you. So all you had was originally it looked like this, the unit vectors, and after transformation, this it looked like this. So x became like this and y became like this. So this was x, this was y, this is x new, and this is y new. So the transformation is basically -90-degree rotation. That's the transformation. There is no scaling happening here. And the next operation is shearing. If you look at this transforming matrix 2 1 1 2, the resultant x new is 2 1, which is the first column, and the resultant y new is 2 2, sorry, 1 2, which is the second column of the matrix A. And when you look at where those x new and y new is lying, so this is y new and this is x new, right? Y new and x new. And if you look at what happened to y new and x new, it's like it underwent 2 operations. It underwent a scaling operation, and it also underwent like a rotation operation simultaneously. So it's almost like shearing. You know what is shearing, right? So if you have originally like a slice of square, like a, let's say, some jelly like this, and if you push it, the shape of the jelly would become something like this, right? something like this parallelogram. So that is what is happening. So originally these grid lines, they were the grid lines corresponding to x and y axis. Now the x-axis, the new x-axis is parallel to this. So if I were to draw parallel lines corresponding to this, it will look like this, and parallel lines corresponding to y would look like this. So this is why we call it as shearing. So if you really look at what's happening to the xy grid, it's becoming sheared. The shearing can also happen in the absence of scaling. Like let's say no scaling is happening. So I'm just deleting these grid lines. So let's say my x new was this, which is almost same length as the original x, and y new was this. Here also basic operation that's happening is shearing. So scaling is not necessary when shearing is happening, but if the rotation is such that the amount by which x and y axis rotate are different. So here in this case, you can see that y axis rotated by maybe plus 30 degrees, and x-axis rotated by minus, let's say, so my signing convention is pluses in the clockwise and minus in the anti-clockwise, but of course depends on whatever your convention is. And here it rotated by minus 30 degree, right? So that's why shearing happened. In the previous rotation example, what happened was x-axis rotated by minus 90 degree, and y-axis also rotated by minus 90 degree. So it was like a pure rotation. In this case, there is shearing. And if the length of these x and y-axis is changing, then it's like a combination of shear plus scaling. So these are the three operations that I want you to be aware of in the linear transformation. So all of these are transformations, all of these are linear. So if shearing is happening, why do we actually call it linear? The logic for that is very simple. Let me just draw that. Why do we call this transformation as linear? It's because, let's say this is the XY grid, right? XY grid, original XY grid. And if I had 2 points here or a bunch of points here, then they are equidistant. And they are also, these lines on which these points are situated, they are also parallel. In the rotation happen, so let's say the operation that is happening to this is scaling. So if it is scaling, it can be squished or expanded. So if it is squishing, these grid lines will come close to each other, right? And then what happens is these points are still equidistant, and the line on which these 2 points are staying, they are still parallel. So this is if scaling is happening. What if what's happening is rotation? Then in that case, if we are doing a 90 degree, let's say 45 degree rotation, then the grid might look something like this, right? So again, these points are equidistant. Previously also it was equidistant, and the line on which these points are situated are parallel. So this is rotation. And let's say we were doing shear, then in that case, let's say this looks like this and this looks like this. Again, the lines on which these 2 points are situated are parallel, and the points are equidistant, these points. So that is shear. So all of these are linear transformation operations for this reason. So it's very important to know the physical intuition behind why we are calling it like this. Now we will look at eigenvalues and eigenvectors from a completely new, fresh perspective. Let A be a matrix 2, 1, 3, 4. The pink color is the first column, blue color is the second column, and let V be the vector, and the vector is 1, 1, column vector 1, 1. What is AV? The matrix multiplication of A with V. What is this? We can calculate it using the trick that we discussed earlier. So the first column will be scaled by this factor. The second column 3, 4 will be scaled by this factor, and you add those two. Because 2, 1 is the transformed unit vector x, 3, 4 is the transformed unit vector y, and the scaling factor for the unit vector x would be this. The scaling factor for unit vector y would be the second element of v. You add those to get the result, which is 1 times 2 plus 3, which is 5, and 1 times 1 plus 4, which is 5. So 5 and 5. And this can be also written as 5 multiplied by 1, 1. And what is that? That is 5v. So if you really look at what the matrix A, this transformation matrix, did to the vector v, it simply scaled the vector. The vector v did not rotate, it did not change the orientation, it simply scaled. And scaling does not necessarily mean always elongating. It can be squishing, it can be flipping the direction. So this constant could be 5 or -4 or -2, anything, right? As long as it's just a constant. And what if we look at another vector here? So let A be same matrix 2, 1, 3, 4, and the vector v is -3, 1. What happens here? Here, AV is -3 times. Here, AV is -3 times 2, 1 plus, so -3 times 2, 1 plus 1 times this 3, 4. And what is that? -6 plus 3, that is -3. And then the second one is -3 plus 4, which is -1. And what is this? This is 1 times v. So again, the vector v is just getting scaled by a factor of 1. So vector v is transformed into vector v itself. So nothing has happened to vector v other than scaling factor being 1. So this is exactly, let's put both of these vectors side by side, v1 and v2. v1 is -3, 1, v2 is 1, 1. The matrix A is 2, 1, 3, 4, same matrix that we discussed before. If we look at what happens to what happens to v1 because of A v1 equal to 1 times v1, and A v2 equal to 5 times v2. We saw these two. Now, you might already recognize what's happening. Matrix A is just scaling vectors v1 and v2. And here, v1 and v2 are examples of eigenvectors of A, right? Because these vectors v1 and v2, A can only scale. And 1 and 5 are the corresponding eigenvalues corresponding to v1 and v2. So now you might be able to think eigenvalues and eigenvectors in terms of transformation. So if A is a transformation matrix, those vectors that can only be transformed via scaling are the eigenvectors of that particular transformation matrix. And the factor by which this scaling happens, it can be positive number, negative number, it can be greater than 1, less than 1. But the factor by which this scaling happens is the corresponding eigenvalue. So I hope this brings you a bit more physical intuition into what is eigenvalue and eigenvector from the linear transformation perspective. Of course, from the mathematics also, this same conclusion can be derived. You don't need all this intuition for that. But it's nice to see this from the fresh perspective of linear transformation. So just to summarize the eigenvalue and eigenvector things. So let's say AV equal to lambda V. Then what's happening to, this is a transformation matrix. Right? This is the vector being transformed. And what is the transformation operation happening here? It's simple scaling. So those vectors which get scaled is the eigenvectors, and the value by which it gets scaled is the eigenvalue. And I guess now the thing is, to calculate this, what we do is, we write it as A minus lambda I times V equal to 0. And then we say determinant of A minus lambda I equal to 0. And those values of lambda that satisfy this condition are the eigenvalues. And those vectors, after substituting those values of lambda in this equation and calculating which vectors give us this condition, those are the eigenvectors. But I guess the important question is, why this? How come determinant of A minus lambda I equal to 0 is, how is that making sense? So why is this the condition that we are mathematically saying that should be satisfied? So we will look at that. And for that, we should have a perspective on what exactly are determinants. So let us look at what exactly is determinant from the linear transformation perspective. Okay. So firstly, let's look at our normal XY grid, right? So we have unit vector in x direction, unit vector in y direction. And if we look at a unit square in this xy grid, that unit square will have area equal to 1, right? It's 1 times 1. Okay, now let's say we have a transformation matrix A that looks like this, 2.5002, right? So what will happen to the unit vector in the x direction? That will become x new, which is the first column of A, and y new will be second column of A, so 0,02. So x new and y new are how the unit vector x cap and y cap will get transformed, right? So now let us see the what happens to the grid. So originally this xy grid, let's say we assumed a unit square in this xy grid, it had an area 1. But now what has happened, this unit square in the grid also got transformed because the unit vectors themselves got transformed. And now it is not a square anymore. It's like a rectangle. And the area of that is 2.5 multiplied by 2, right? The area of this is 2.5 multiplied by 2, which is 5. So can you see now what happened to the area? The area basically got scaled by a factor of 5. And can you also see quickly what is the determinant of A? The determinant of A is 2.5 multiplied by 2 minus 0 times 0. So it's 5. So determinant is basically the scaling factor by which the original unit square in the xy grid gets transformed to. So that is the determinant. And what if the transformation instead of, so this is like a scaling. These vectors are just getting scaled. What if there was a little bit of rotation or shear? We can see in that case also this thing holds, like the resultant, the unit square will become looking like a parallelogram, and the area of that parallelogram would be the scaling factor for what's happening to this unit square in terms of area. And that value will be same as the determinant of this matrix, transformation matrix A. So the insight that you should understand is determinant is the area scaling factor. Now, the important thing is, in some cases, right? In some cases, the area can get scaled by 0. Let's see what is that case. In what case can that happen? So let's say the transformation matrix is first column is 2, 2, second column is 2, 1, 1. In this case, determinant is obviously 2 times 1 multiplied by 2 times 1 minus 1 times 2, that is 0. So determinant is 0. But can you also see where is the x new and y new? X new is 2, 2 and y new is 1, 1. So what this means is we are, just have a look at this. I'll go back. The new x, which is x new, is this pink line from origin, and the new y is 1, 1, which is this. Now, where is the area? What's the area of the unit square in this? Area is 0. Do you see why? That's because we can just draw it so that you can understand. So let's say the transformation happens such that I'll just create a duplicate of this slide just to explain this. So let me just delete all of this. Okay, so let's say this was the transformed vector, both of the vectors. Then what happens to the unit square? The unit square would look like something like this, somewhat, right? The unit square gets transformed to this parallelogram. If it was not a so this is a shear operation, shear plus linear transformation, linear scaling. What if there was only linear scaling? That we saw already. That in that case, we had the parallelogram. Instead of parallelogram, we had a square. That's what we saw in the previous slide. We had this square. But now let's say our scaling is such that, so this parallelogram has a finite area, and maybe that area is greater than 1, maybe it's less than 1, depends on how the parallelogram's shape is. What if these two vectors are so close to each other? In that case, how would the parallelogram look like? It might look like this. So now the area is getting smaller and smaller. What if they both align completely on top of each other? The size can be different. Maybe the size of one can be different than the other. Then what's the area of the resultant parallelogram? It's 0. So what happened to this initial unit square? The unit square, which had an area of 1, it got transformed into a shape which has a 0 area. So, and of course, you can guess what is the determinant of the vector that makes it possible. Sorry, the determinant of the matrix that makes it possible. The matrix was 2, 2, 1, 1. X nu was, this 2, 2. Y nu was this 1, 1. And determinant of this is obviously 0. So when determinant becomes 0, the area scaling factor is also 0. So that's so beautiful, right? So that is the physical intuition behind determinants. And if we take any other vector parallel to this x nu and y nu, so this is x nu, this pink line, this is y nu, and this is the case where the matrix which is transforming x cap and y cap into x nu and y nu has 0 determinant, right? That's why these two things became parallel. Now, what happens to another vector that is parallel to x nu and y nu? We know that any other vector along this line can be represented in terms of x nu and y nu. We know that, right? So let's say the vector v is 3, 3. Then AV equal to 3 times 2, 2. Sorry. Over here, AV equal to 3 times 2, 2 plus 3 times 1, 1, which is 9. So this is 3 times 2, 6 plus 3, 9. And the bottom element is 3 times 2, 6 plus 3, 9. So that is 3 times 3, 3, which is 3V. So did you see what happened? So what happened is, if because determinant of A was 0, the x nu and y nu were on top of each other, parallel to each other. And now because V is also oriented on top of this, so V will look like this, right? The vector V is over here. That vector V we can represent in terms of the after transformation in terms of the original vector V itself. So the A is just linear, A is just scaling the vector V, right? A cannot rotate the vector V, A cannot shear or do anything else. A is just scaling the vector V. So now here you can see that here if A is a transformation matrix and if V is a vector and if 3 is a constant, then for this transformation matrix, V is an eigenvector and 3 is an eigenvalue. So now we can easily relate this back to our original determinant of A minus lambda V equal to 0. So I'll come to that in a moment here, but just notice that V just got scaled. Nothing else happened to V. So similarly, now let's come to the original thing that we were discussing, eigenvalues and eigenvectors. We have A times V equal to lambda V, and then this we write as lambda times I times V because we want the matrix representation instead of just scalar multiplication. Then we write like this. So we don't want trivial solution. We don't want the vector V to be 0. That's trivial. We don't want A minus lambda I to be a null transformation matrix. Basically no transformation happening, like a null transformation happening. So what this means is determinant of A minus lambda I equal to 0. Why is this the case? This is the case because of the following reason. So A minus lambda I times V. So here, this is the transformation matrix. We can call this as B and B times V. So we want this equal to 0, this equal to 0, right? And, but before considering this, let's think about what B does to the unit vectors x cap and y cap, right? So something will happen. So B times x cap will be some sort of x nu, and B times y cap will be y nu. And what we are saying is the vector V is getting transformed into 0 by this transformation matrix. What that means is we knew that let's say this was not 0. Let's say BV, let's say our goal was just to calculate BV. How would we have done that if V equal to, let's say V equal to V0 and V1, if this was V, how would we do this? And let's say B equal to, I'm just writing B11, B12, B21, B22. Maybe for simplicity, I'll write this as V1 and V2 rather than V0 and V1 and V2. Then BV we would have written as V1 times B11, B21, right? Transformation matrix is B. So this is the first column of transformation matrix that will be multiplied by V1 plus this is the second column of transformation matrix. So B12, B22, this will be multiplied by V2, right? This is what it would have been. And what we are saying is, this is what? This is X new and this is Y new. And what we are saying is this is equal to 0. So BV equal to 0. Now, can you think, what does this mean? When can this happen? When can two non-zero vectors, so now what's happening is 0 equal to V1 times X new plus V2 times Y new, right? And we had already said that we are not interested in trivial solution. We are not interested in the case where V is a null vector, or we are not interested in the case where B is a null matrix. So the only case in which V1 times X new, which is a vector, and V2 times Y new, which is another vector, will be 0 is when these two vectors are like cancelling each other if they are non-zero. And when will they cancel each other? They'll cancel each other if X new and Y new are parallel or anti-parallel. They should lie on the same line, right? So what this means is BV equal to 0 means B will transform X and Y to X new and Y new such that X new and Y new fall on the same line. And so what does this mean? What does this mean is, if they fell on the same line, you would remember from the previous slide, from this slide, if X new and Y new fell on the same line, then this happens when the determinant of the transforming matrix is 0. So here the matrix name, the name of the matrix which was making this transformation happen such that X new and Y new were falling on the same line was A, but in our case it's B. So here what this means is if B is transforming X new and Y new such that they are falling on the same line, the only thing that means in non-trivial cases, determinant of B equal to 0. I hope you're clear about why X new and Y new are falling on the same line. If it's not clear, I can just quickly tell that. So if we assume that B is this non-zero matrix and V is this non-zero vector, then BV we can write in this following way, right? BV is V1 times so V1 times the first column of B plus V2 times second column of B, and first column of B is essentially X new, right? This we already discussed. Second column of this B is Y new, and so this whole thing becomes. Let me just add one more page. BV equal to what is that? V1 times X new plus V2 times Y new. X new plus V2 times Y new, right? This is how it is. We are saying that X new not equal to 0 and Y new is also not equal to 0. So what this means is if these two vectors are cancelling each other out, so V1 X new means X new is getting scaled by a scalar. So let's say this is X new, and let's say Y new is this. So let's say length of x new is 1, length of this thing is minus 3 in this direction. Then this can, so this is minus 3 in now we can say that 3x new plus y new equal to 0, right? So the way in which BV can be 0 is when these two things are parallel, and when those two things are parallel, determinant of B will be 0. Now what is B? We had called A minus lambda I times V equal to 0 is where we started, and this we called as B, BV equal to 0. So if determinant of B is 0, then determinant of A minus lambda I equal to 0. So this is what it means. So the reason why we are saying while calculating the eigen values and eigenvectors, the determinant of A minus lambda I equal to 0 is because if A minus lambda I we consider as a whole matrix which is transforming the xy space, the transformation happens in such a way that the x and y axis will fall on the same line after the transformation, and because of that reason, the scaling factor of the area of the unit square will be 0. So the unit square will become like almost like a straight line. So the area of that would be 0, and because of that, the determinant of the transformation matrix, which is A minus lambda I, will also be 0. So this is how it works. Now there are a few interesting things that we can look at. How about, let's say let's say A equal to 1 0 0 1. This is identity matrix, right? Can you tell what are the eigenvalues and eigenvectors of the identity matrix? The eigenvalues and vectors of identity matrix are all possible. Eigenvectors are all possible vectors in the xy space. So if we take any random xy 5 3, then A times 5 3, so A is 1 0 0 1 equal to let's say this is V equal to AV equal to V itself. So lambda equal to 1. So here, if identity matrix is what the operation is, then in that case, lambda equal to 1, V equal to all vectors in xy plane. Okay, so this is good. What about transformation matrix being 2 0 0 2? What about this? This we can write as 2 times I. So now AV equal to 2 times IV, and this equal to lambda V, which is equal to 2V, right? And so here in this example, lambda equal to 2 for all V, where V is any vector in the 2D space. I mean, this same thing is applicable for 3D, but we are restricting all of our discussions to 2D space. That's why I'm not talking about 3D now. But basically, any vector in 2D space is the eigenvector for this matrix, transformation matrix A, and the eigenvalue corresponding to that operation for any vector is 2. So essentially, here, like if you take any vector, the only thing that happens to that vector, if this was the original vector, the only thing that happens to the vector is it will get scaled by a factor of 2. In the previous case, if this was the xy space, right, the only thing that happens to this vector is it will just get multiplied by 1, so it will stay there itself. Let's look at another case, right? How about something like this? Let's say matrix 2. Let's look at the rotation transformation. So it was 0 1 and minus 1 0. So here the x-axis, which was this, would become something like this, and y-axis, which was this, will become something like this. So here what's happening is the the matrix A, the transformation, what's happening is rotation. Do you see why that is? I'll just show you. So let's say this is the x-axis. This is the x vector, and we have the y cap here. So what is the x nu in this case? X nu equal to 0, 1, the first column of the transformation matrix. Y nu equal to -1, 0, right? So x nu is 0, 1, which means this is x nu. And y nu is -1, 0, which means this is y nu. So all that happened is a 90-degree counterclockwise rotation. That's what happened. So can you think of any vector which, because of this rotation transformation, after rotation, the vector should only get linearly scaled. The vector should not, rotate. Can you think of any vector where this is possible? You can already see that for no vector this is possible, because no matter what's the orientation of the vector, that vector is going to be rotated by 90 degree. So what that means is, what if we do the calculation, right? A minus calculation of A minus lambda, like this, A minus lambda I, determinant of this equal to 0. So A minus lambda would be -1, -1, 1, 0. Oh, sorry, minus lambda, 1, 0. Determinant of minus lambda, -1, 1, minus lambda. This should be equal to 0. And what's the equation for that? Lambda square plus 1 equal to 0, which means lambda equal to plus or minus I, imaginary number. So what this means is there does not exist a real vector that does not undergo rotation transformation. So that's the meaning of this. And there are several other such interesting cases also. So I hope you understand the physical reason for this. Like when you are rotating the whole xy plane by 90 degree, you can't have any vector which just scales by itself. Like how do you scale if your entire xy coordinate system is being rotated by 90 degree to the counterclockwise direction? You cannot come up with any vector which does not undergo that transformation. So that is the reason for that. So what if the vector A is just the matrix A is just a diagonal matrix 2, 0, 0, 3. Can you guess what would be the eigenvalues of this? It's fairly simple. The logic is the following, right? So if this is what is the vector looks like, sorry, the matrix looks like, then the transformation that is happening is x prime will become x nu, which is equal to 2, 0, and y hat will become y nu equal to 0, 3. So do you see what's happening to x nu? What's happening to x nu is it's like 2 times x hat, and y nu is 3 times y hat. So now you can already see that since x nu and y nu are now aligning, so x nu is if this was x hat, x nu would be this, right? 2x hat. And if this was y nu, sorry for my handwriting, I'm just writing fast here. This is 3y hat, which is this is y hat, and this is y nu. So they are aligned again on top of each other. So what this means is any vector that is along the x-axis will get scaled by a factor of 2. Any vector along this axis will get scaled by a factor of 3. So 2 and 3 are the eigenvalues, and any vector that has a shape which looks like a alpha times x hat, these are the eigenvectors which has eigenvalues of 2, because they will get scaled by a factor of 2. And any vector in the form of beta times y hat in this format, which this will get scaled by a factor of 3. So the eigenvalue is 3. So basically the eigenvalues of a diagonal matrix will be those diagonal values themselves. So this is an interesting insight. So just think about that a little bit. So hopefully this gave you some good physical insight into what's happening in when you are calculating eigenvalues and eigenvectors. It's all about linear transformations happening in that space. It can be an n-dimensional space. So we selected two-dimensional space because that's the easiest thing to show on a like a 2D board. But the same concept applies across 3 dimensions or any number of dimensions. So just try to understand eigenvalues and eigenvectors from this perspective, and that will easily tell you when you're studying in your course that, oh, for a diagonal matrix, the diagonal elements themselves are the eigenvalues. This is the reason for that. The reason is that here the x and y axis are getting scaled by a factor of 2 and 3, which means any vector which is along the x-axis will get scaled by a factor of 2. Any vector that is on the y-axis will get scaled by a factor of 3. So it's as simple as that. So I hope this lecture gave you some good idea about the physical intuition behind eigenvalues and eigenvectors. And feel free to let me know your thoughts. And we'll be in this linear algebra lecture series, we'll be posting more such videos. So thank you so much, and we'll see you again in the next lecture.